Okay, welcome back. This is section 4.2. We're talking about some composition and inverse functions and relations. In this video, we are going to talk about how to write a function that combines other functions, how to use a graph or table to determine values of the function's inverses, how to find the inverse, how to restrict the domain of a function whose inverse may not have been a function, so that way we can create a function, and how to use composition of functions to determine if two functions are actually inverse. Okay, so what exactly is an inverse? We keep talking about composition. The inverse is, by definition, the set of ordered pairs obtained by exchanging the coordinates of each ordered pair. So that means, basically, if AB is an ordered pair, so if A is your input and B is your output, then in the inverse, B is the input and A is our output. We write an inverse using this notation right here. Please do not confuse this notation. This is not an exponent. We're not talking about x to the negative 1 being 1 over x. That's not what this is about. This is not an exponent. It is the notation for an inverse function. So we read it as the inverse of f of x. The inverse of f of x, and that's how we read it, as the inverse of f of x. If both a relation, f of x, and its inverse, the inverse of f of x, are actually functions, then we can call them inverse functions. So if we're just talking about relations and we want to write the inverse of a, again, if AB is your relation, then BA is the inverse. So if 1, 5 is the relation, then 5, 1 is the inverse point. If 2, 6 is A, then 6, 2 is the inverse point. If 3, 7 is A, then 7, 3 is your inverse point. Let's take a look at the domain of A and B. So the domain of A is the points 1, 2, and 3. And the range of A are the points 5, 6, and 7. The domain of B, remember, is the input, so 5, 6, and 7. And the range are the outputs, 1, 2, and 3. And so we notice that they've switched. The domain of A is now the range of B, and the range of A is now the domain of B. And that makes sense because if we're switching x and y, and domain was what all the x's are, and range is what all the y's are, then they would also switch. So by definition, if f, a function, and its inverse function are both inverses, then f of A equals B if and only if the inverse of B equals A. In practice, what this means is if we have f of x is this function, and the inverse of f of x is x plus 4, then if I evaluate f of 6, so that means put in 6 for x, so 6 minus 4, of course, is 2. So if f of 6 is 2, then we can assume then the inverse, if I put in 2, I should get out 6. And so I can evaluate that to check and see if that works. And so if I put in 2, so 2 plus 4 should equal 6, and in fact it does. And this is because these are inverse functions. So if we look at this on a graph, okay, if we start by graphing y equals 2x minus 4. So we're going to go down 4, and then we're going to follow the slope. And when we graph this, we can pick a couple different points. So negative 1, negative 6, 0, negative 4, 1, negative 2, 2, 0, 3, 2. And we can use the definition of inverse to write the points that should be on our inverse function. So if 1, 6 is the original function, then negative 6, negative 1 is the inverse. If 0, 4 is the original relation, then 4, 0 should be in the inverse. And so we end up with negative 2, 1, and 0, 2, and 2, 3. And so we're just switching the x and y values. And when we graph these points, we notice that that also draws a line. Specifically, it draws a line with a y-intercept of 2 and a slope of 1 over 2. So that would have an equation of y equals 1/2 x plus 2. And so the question is, can we find this equation from this equation? Well, by the definition of inverse, we are switching the input and output values. So what would happen if I switched the x and y? So if x equals 2y minus 4, can I rewrite this equation so it matches this equation? Well, this equation has been solved for y, so let's do that. If we add 4 to both sides, we have x plus 4 equals 2y. And if we divide by 2 on both sides, then we end up with 1/2 x plus 2 equals y. And indeed, that matches the equation for the line that we drew from the points that we switched around. When we look at this, it looks like they cross at a very specific point, and in fact they do, because all inverses are a reflection across the line y equals x. All inverses are a reflection across the line y equals x. Okay, took a moment to go ahead and graph that function, use the points to find the inverse, also find the inverse function. Okay, welcome back. Here are the answers. So here's the graph of the first function with the domain and range, the graph of the second function. Okay, so we discovered that if we switch the x and the y and we solve for y, we can find an inverse relation. So if we rewrite this as y equals x squared minus 1, and then we switch the x and y values, so we rewrite it as x equals y squared minus 1. We solve for y, so add 1 to both sides, x plus 1 equals y squared. If we take the square root of both sides, we consider the positive and negative form. So now we have y equals the positive or negative square root of x plus 1. Now, in this case, we have a square root, which means what's in the square root has to be greater than or equal to 0. That is, x has to be greater than or equal to negative 1. So we're going to have to restrict this domain to say that this is the inverse as long as x is greater than or equal to negative 1. Go ahead and try this next one. Remember that we switched x and y and solved for y. Okay, welcome back. Here's the answer and our next problem. Okay, so what if we're talking about graphs? So what is the graph of x squared minus 1? Well, we know x squared minus 1 is a quadratic, so it has a vertex at 0, negative 1. And so we can find the points at negative 1, 1. And rather than 2, because 2 is going to be kind of short, I'm going to go up to negative 3 and 3, because that might help us. And when we evaluate those, we end up with 0, 0, and negative 3 squared is 9, and so 8 is the y value here, and so we can graph that, and it looks like this. And our domain include all x values, right, all real numbers, and our range is from negative 1 to infinity. And so if we switch those points, so the inverse of that should be at 8, negative 3, 0, negative 1, negative 1, 0, 0, 1, and 8, 3. And when I graph those points, I can see that I end up with something that's not a function. In fact, it's a relation. That relation does have a domain and range, and specifically, if you look at this, the domain, the x values start at negative 1 and go off to infinity. And the range here goes down forever and up forever, so the range is all real numbers. And we notice again that the domain of the original function becomes the range of the inverse, and the range of the original function becomes the domain of the inverse. And again, we can see that still this is a reflection across the y equals x line. Now, we remember the vertical line test, right, that tests and tells us that this is indeed a function. And the vertical line test tells us that this is indeed not a function, because when you draw a vertical line, you end up with two y values for each x value. So is there a way to make this an inverse function? Well, let's look at what we know about functions and inverses first. The graph of the inverse is a reflection of the graph on the line y equals x. We also know that just like the vertical line test is used to determine if a graph is a function, we can use the horizontal line test to determine if a function is one-to-one. Well, if a function is one-to-one, then if we switched it, wouldn't its inverse also be a function? And in fact, that's the case. So if a function is a one-to-one function, then its inverse will also be a function. So that is, if an original function passes both the vertical and the horizontal line tests, then we know that its inverse is going to be a function. Now, if the inverse is not going to be a function, we can restrict the domain of the original function. So that is, we kind of say, okay, we're only going to take this piece, kind of like you did in your animal equations project. We're only going to take this piece of the function, and that way it is forcing it to be a one-to-one function. Okay, let's go back to our example 8. We notice in this that our original function is actually a function, but its inverse is just a relation. Well, is there something that we can do to the original function to force its inverse to also be a function? And if we look at only half of the original function, which means we look at the domain only from when x is greater than or equal to 0, now we have a one-to-one function, which, when we find its inverse, meaning our range is going to then be from 0 to infinity, and only that part of the inverse function. And now instead of being a relation, so basically we're getting rid of the negative part, now we have an inverse function. Okay, so let's take a look at the function f of x equals the square root of x minus 2. What are the domain and range of f? Well, if we graph the function here, we know that it's a translation of the square root to the right 2. So we graph this, and we notice that the domain is 2 to infinity. 2 to infinity. So 2 to infinity. And the range is 0 to infinity. So if we wanted to find the inverse of this function, so we write it as y equals the square root of x minus 2. If we were to switch the x and y, so x equals the square root of y minus 2. If I were to square both sides, now I have x squared equals y minus 2, add 2 to both sides, and x squared plus 2 equals y. However, this would only work if x is greater than or equal to 0, because when we look at this, the original function is here. If we graph this quadratic, then we're going to end up with more than what we had in our original function. So we need to restrict this x value for only be greater than or equal to 0, so that the domain of the inverse matches the range of the original function. And so there's our inverse function. Okay, go ahead and try this. Pause the video and we'll be right back. Okay, welcome back. Here are the domain and range. And when you found the inverse function, this is the function you should have found, which has a domain of this. And yes, of course, g is a function. Okay, so how do we know if functions are inverses? Well, first, let's consider known inverses. I know from the example that I did a moment ago that the square root of x minus 2 and x squared plus 2 are inverse functions. So let's take f of x as the square root of x minus 2 and the inverse of f of x, x squared plus 2, and do some composition. So if I put in the inverse, which is x squared plus 2, as an input in the original function, so that is I take the square root of x squared plus 2 minus 2. So I put in what was my input. Well, and I simplify. So 2 minus 2 is 0, so I'm taking the square root of x squared, which of course is x. Well, what if I go the other way? What if I want to find the inverse of f of x of f of x? Well, again, f of x is the square root of x minus 2. And the inverse function says take it, square it, and then add 2. So take your input, square it, and add 2. And so if I have the square root of x squared minus 2, the square root of anything squared is just itself. So I end up with x minus 2 plus 2, which is x. And so we find that f of x and g of x are inverse functions if their compositions result in the identity, or x. So that is f of g of x equals x, and g of f of x equals x. And specifically, you must check both compositions to make sure that they are actually inverses. So let's try one more problem. So let's say f of x equals 3x plus 9, and g of x equals 1/3 x minus 3. Let's find f of g of x. So if f of x is in blue, and g of x is in red, first I'm finding f of g of x, and g of x is 1/3 x minus 3. And f of x says 3 times whatever your input is plus 9. So I put g of x inside as the input, distribute the 3. So 3 times 1/3 is just 1x. 3 times negative 3 is negative 9 plus 9, and I get x. I can do the same thing for g of f of x. So in this case, I'm going to take g of f of x, and so f of x is 3x plus 9, and g of x says take 1/3 of your input and subtract 3, and your input is 3x plus 9. So when I distribute the 1/3, 1/3 times 3x is x, 1/3 of 9 is 3, minus 3, which is x. And so the functions are inverses because f of g of x equals x, and g of f of x equals x. Okay, go ahead and try this and unpause the video when you're ready. Here is the answer. Okay, thank you so much for listening. Up next, you need to finish the reflection for this section, and then we're going to be talking about nth roots and radical expressions in the video. Thank you for your time.